Welcome back to the last lecture set, if you will, or the last lecture part in chapter 3. I'm actually kind of glad, in a way, that we're doing this online because we can easily break up these sections of lecture into three more reasonable bite-sized parts, I guess, as opposed to just sitting in a lecture for 2 hours, going from start to finish on this chapter 3. One thing I don't like, though, is that I can't be there with you guys to help walk you through these different equations and things like that, and how to calculate this. So we finished off on part 2 talking about what we can do with mass percentages. And so what I want to do is take the time now to go through a couple different things with regards to how we can determine empirical formulas from given a mass percentage. So I'm going to do one on the board. And then I want you guys, I'm going to give you guys one to do that I would like you guys to do on your own, and giving you just a couple things to really think about as we're doing it. And then I will walk through one about a combustion analysis, right? How we can use a combustion analysis, which is a way we can determine mass percentages to find an empirical formula. So the goal is to find an empirical formula. That's the goal of all these different calculations. And then what we'll do at the end is we'll talk about balancing equations. And then what we'll do is after we talk about balancing equations, I'll make a couple of notes on things that we might want to continue to think about and to keep in mind, especially when we do some calculations with mass percentages. But we'll save that for the end. All right, so let's go to the board. So I've already written a problem on the board, and vitamin C, for those of you guys, my handwriting is a little bit messy. Vitamin C is 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. And so what I want you to do is we're going to look and calculate the empirical formula for vitamin C, also known as ascorbic acid. So let's think about what we have. And what we have are percentages. What do you think we might need to start calculating that empirical formula? Well, how much of the sample do we have, right? How much, so we know within a sample there's these percentages. Well, how much of the sample do we have? Well, it's not given in this problem. If you were asked to find an empirical formula and you're given the percentages without a mass, go ahead and assume 100 grams, right? That's a lot of grams, but if we assume 100 grams, it makes the math a lot easier. And so what do I mean by making the math a lot easier? So if we have 100 grams of total sample, how many grams of carbon are in this sample of vitamin C just by looking at the percentages? That's right, 40.92 grams. And then how much hydrogen? 4.58 grams. And then how much oxygen? 54.50 grams. Okay. So to find an empirical formula, oh, that's really low. Okay, so I'll try to walk through the oxygen a little bit. Maybe I'll bring the oxygen up later. But what we need to do, so now we know how many grams of the atoms or the elements that we have. We need to now turn them into moles. So let's think about this because we covered this in chapter 2. If we're going from grams to moles, we're going from something bigger, a bigger unit, to a smaller unit. So we're going to divide. Well, what do we need to divide by to go from grams to moles? And that's the molecular weight. And so for carbon, it's 12.01 grams per 1 mole. For hydrogen, it's 1.01 grams per 1 mole. And then for oxygen, it's 16 grams, I know you can't see it, per 1 mole. Right? And so we have 16 grams, so it'll be 54.50 divided by 16 grams. So let's go ahead and see this. So for the carbon, so we do that, we get 3.407 moles. Again, remember, round out at the end. Hydrogen is going to be 4.54 moles of hydrogen. And then oxygen, oxygen is going to be 3.406 moles of oxygen. Right? And so now we have we have the moles of carbon, we have the moles of hydrogen, and we have the moles of oxygen. So when we work on an empirical formula, we now have everything we need to solve it, right? So we need to find the moles. And here is why. So let's look at what an empirical formula might look like. So we know ascorbic acid has carbon, hydrogen, and oxygen. It doesn't matter the order with which you place these. I just usually do carbon, hydrogen, and oxygen. So how many moles did we find out of carbon are there? 3.4. How about hydrogen? 4.5. And oxygen is 3.4. Now, those little subscripts that we talk about when we did our naming, when we looked at these molecular formulas, those are the number of moles of the atom within this compound, right? So here you have two things of carbon. You have 2 moles of carbon for every 1 mole of ascorbic acid, right? And so that is known as a molar ratio. Molar ratios are going to be very, very important in chapter 4, and then even here in chapter 3, and a little bit into chapter 2, when we talk about, well, let's say we want to know how many atoms of magnesium are in magnesium hydroxide. Or let's look at this. How many moles of carbon are in this compound here? Well, you would say for every 1 mole of the compound, we would have maybe 1 mole of 2-3 moles of carbon, whatever we decide this to be. So let's do the empirical formula. So right now we have these number of moles from down here. The next step is then to divide by the smallest number. Right? And so here we're dividing by the smallest number, which is 3.4. And what will happen is we'll get C1H 1.301. Now, what did we say when when we talked about the atomic theory about whole numbers in compounds? That atoms bind together in whole numbers to form a compound. 1.3 is not a whole number. So what do you think we need to do to turn 1.3 into a whole number? What if we multiplied everything by 3? Obviously, I understand this will turn into like 3.999999. That's close enough to 4 in this case. So we have C3H4O3. That is the empirical formula for vitamin C, ascorbic acid. So for every 1 mole of ascorbic acid, we have 3 moles of carbon, 4 moles of hydrogen, 3 moles of oxygen, right? And so that's how we can kind of read this equation. So this is the empirical formula, right? And we talked about molecular formula showing us the total number of molecules. So what would be the molecular formula of ascorbic acid? What do you think we would need to know to calculate that? Yes, we would need to know the molecular weight. So I will tell you the molecular weight of ascorbic acid is 176.12 grams per mole. So the way we calculate the molecular formula is we take the molecular weight and we divide it by the empirical weight. The empirical weight is the weight of this thing over here. When we calculate it, it's at 88.07 grams per mole. And we divide molecular weight by empirical weight, we get a number N, which is going to be 2. And so what we can do is take this 2, and we're going to multiply it by our empirical formula. And so the molecular formula is going to equal C6H8O6. That is a lot of work. It is a good amount of work. It is. If you wanted to check your answer, you can calculate the molecular weight of this, and it should match up very similarly to that. Usually in compounds, hydrogen with carbon and oxygen, hydrogen, there's more hydrogen than those. So that looks good. It's just going to take a step-by-step procedure, just like we did. We found the grams, we went to the moles. Once we found the moles, we can plug it in here, we simplify it. If we have to multiply by a factor to get all the whole numbers, we do that. There's the empirical formula. If I were to just ask on an exam, what's the empirical formula given these numbers, this would be your answer right here. Now, I want you guys to try this one on your own, just so that we can, so that, again, in the sake of practice, right? So that you guys can try it. And then if you have any questions, you can just say, hey, Dr. Bishop, I tried this. This is where I'm getting stuck. So there's a thing called methyl benzoate, and you have 5.325 grams of methyl benzoate, right? So we have methyl benzoate, and you have 5.325 grams of that. You have 70.6% carbon, 5.9% hydrogen, and 23.5% oxygen. And I would like you guys to figure out the empirical formula for this methyl benzoate, just given this information. So you're given grams and you're given percentages. Now, I want to say hypothetically, let's say I didn't give you the oxygen. I want you to think about, we're not going to solve it this way, but I want you to think about, well, how would I solve it if I wasn't given the oxygen? I want to think about how to solve it if I wasn't given the oxygen. But you are, so now just go ahead and solve it like this. All right, now let's say we're given a compound that smells like pineapples. Ethyl butyrate is this compound. And what you do with ethyl butyrate is you combust, let's see if I have different, nope, okay. Is you combust 2.78 milligrams. So I'm going to throw a wrench in here with the milligrams. So you have 2.78 milligrams and you combust it, right? So this is a type of analysis where you take a sample and you burn it and you measure the products. And here's the products of a combustion. You get 6.32 milligrams of carbon dioxide, and you get 2.58 milligrams of H2O. Now, if you are thinking, wait, Dr. Bishop, there has to be the same mass on the left as there is on the right. In a way, yes. But what we're doing in a combustion is we're adding oxygen to the mixture. And so the masses over here will be a little bit more than what you started with, and that's okay, right? And so this is our product. This is our product that we burn and that we want to find the empirical formula for. So how in the world do we need to start this problem, right? Because that's the question. What do we need to do to start this problem? Well, let's think about what we need to find first. What did we find first in the last problem? Right, when we were just given the percentages. Right, we found the moles. So let's start with the moles. Well, here we have CO2 and we have H2O, right? And I'll tell you that ethyl butyrate is carbon, hydrogen, and oxygen, right? So it has carbon, hydrogen, and oxygen in it. Okay, well, there's oxygen in here and oxygen in here. So I don't think we could probably do that first, right, to find the number of moles, because there would be a lot of stuff we'd have to factor in. Let's start with carbon, because there's only one carbon here, right? It's C1O2. So let's start with carbon. So moles of carbon are going to equal. So we're given the milligrams of CO2. Ooh, milligrams. Well, we've only been dealing with grams. So let's convert milligrams into grams. So for every 1 gram, remember, we're going from something smaller to something bigger. So we need to divide. when it comes to converting milligrams into grams, right? So there's 1,000 milligrams, so we need to cancel the milligrams in every 1 gram. Well, how do we go from grams to moles? That's right, we divide by the molecular weight. Now, here's where we need to learn that molar ratio that I talked about in the previous example. For every 1 mole of CO2, right, because this is still CO2 that we're talking about. So for every 1 mole of CO2, and I'm sorry, I'm running off the screen again, I think, how many moles of carbon are there? Exactly, there's 1. So for every 1 mole of CO2, there's 1 mole of carbon. That's why we start, whoop, lost the board. That's why we start with CO2. And so when we do this calculation, right, so you're going to take 6.32 divided by 1,000 times 44.01. You're going to get 1.4 times 10 to the negative 4th moles of carbon. Okay? So now, let's talk about moles of hydrogen. Because now we can do moles of hydrogen, right? Because it's in a unique thing. And we're going to solve it exactly the same way. 2.58 milligrams of H2O. The molecular weight will change because we're talking about water instead of CO2. So it's 18.02 grams for every 1 mole of H2O. Now, here's where we need. For every 1 mole of H2O, how many moles of hydrogen are there? So for every 1 mole of H2O, there are 2 moles of hydrogen. Right? And again, I know what you guys are thinking. Oh, Dr. Bishop, this is a little bit of work. This is a little bit of work. I would agree. The way we're going to do this is with practice, and just doing a couple problems. And again, it's just all grams to moles, moles to grams, right? Where we're seeing this pattern here. This one is 2.9 times 10 to the negative 4th moles. Whoops, you can't see that, but 2.9 times 10 to the negative 4th moles. All right, so we know we have C and an H and an O. Well, right now we know, I'm going to go ahead and erase this stuff. We know how many moles of carbon we have, and we know how many moles of oxygen we have. So let's think about how we find out the moles of oxygen. Well, we can't directly calculate the moles of oxygen, so let's convert this. So we have 1.4 times 10 to the negative 4th moles of carbon. And we're going to go 1 mole of carbon is 12.01 grams of carbon, right? And we know in 1 gram there's 1,000 milligrams. And so what we're going to find now is the milligrams of carbon, which is 1.68 milligrams of carbon. And I'm going to show you why we're doing this in just 1 second. So then let's do it the same thing for hydrogen, right? 1 mole is 1.01 grams, and then 1 gram is 1,000 milligrams. Just to let you guys know, when I do this equations or when I do this math on the board, I move pretty quickly, just so that we can get through it. So I might make some jumps. If you're going through it again, taking notes, and you're thinking, wow, I don't know how he got there, just ask me. Take a picture of your notes with a circle on it and say, Dr. Bishop, I don't see this right here. And then I'll help explain it to you a little bit better maybe. And so we have 0.29 milligrams of hydrogen. Okay, well, these two, if we add them together and we subtract them from that, what's left over? The milligrams of oxygen. And so what we do is when we do that, when we take this plus this minus this, we get 0.81 milligrams of oxygen. So what we can do is we can take this and we can do our conversion into moles. And you guys, I would like you guys to go ahead and do that, just so that you can see, again, going from milligrams, the same way we did it for the carbon and the hydrogen, take the milligrams into the moles. And what we're going to get, it's going to be 5.1 times 10 to the negative fifth moles. See if you get that answer. All right, so we have moles of carbon, we have moles of hydrogen, and we have moles of oxygen. What are we ready to do? Finally. I know what you guys are thinking. Holy cow. So let's do carbon is 1.4 times 10 to the negative fourth. Hydrogen is 2.9 times 10 to the negative fourth. And oxygen is 5.1 times 10 to the negative fifth. So which one is the smallest? It's oxygen. So I'm just gonna, instead of doing times, I'll do it, times 10 to the negative fifth, times 10 to the negative fifth, times 10 to the negative fifth. What we end up with is C 2.75 H 5.701. So we end up with C 2.75, H 5.7, and O1. What whole number can we multiply those by to get a nice even number? Yeah, I don't know either. So we're just going to round up C3, H6, O. And that is the empirical formula. Whew. What a problem. And those problems are probably the hardest and just the time-consuming problems. But we can do it, and we need to do it. It's very important that we do it, because again, it just gives us practice going from moles to grams and grams to moles. Now, the one last thing that we have to cover here is when chemical formulas are determined, we can start to write chemical reactions. And chemical reactions are a process where we change one substance into another. We have products and reactants. I like the one, the 2 cracker squares plus 1 marshmallow plus 3 chocolate squares equals 1 s'more, right? Completely balanced equation, perfectly balanced equation. The tip I'm going to give you, and I guess we'll answer the question first, why do we need to balance our equations? Because Antoine Lavoisier said so. So I want you guys to think about when we balance an equation. I'm going to give you an example of it, and one way we can think about this. When we need to balance our equations, we need to balance oxygen last, right? Because if you start with oxygen, it's going to be a bad thing. You can start with anything else, just do not start with oxygen. So let's, one more time, I know I apologize for this video running a little bit longer, but let's go ahead and look at just a way that we can balance an equation. An easy way that we can balance an equation. And again, doing it this way, if you're already a pro at balancing equation, then you can probably turn off the video right now. If you want just a different way to look at balancing an equation, then go ahead and leave the video up. So let's do aluminum hydroxide. So AlOH3 solid plus nitric acid HNO3 goes to aluminum nitrate. I'm gonna run out of room. Plus, yeah, we're good. Water, H2O. Okay, so here's how I start balancing equations. I do a general housekeeping. So we have aluminum on this side, hydrogen, hydrogen, oxygen, oxygen, nitrogen, nitrogen, right? You can put those in any order you want. If you want to put oxygen at the last so that you remember to do oxygen last, that'd be great. So we have 1 aluminum, we have 4 hydrogen, 3 here, 1 here. We have 6 oxygens, right? Because there's 3 here and there's 3 here. And then we have 1 nitrogen. Let's look over here. We have 1 aluminum. We have 2 hydrogens. We have 9 oxygens, right? 3 times 3. And then we have 3 nitrogens. So let's think about how we're going to balance this equation. So what do you want to start with? Nitrogen? Perfect. Let's start with nitrogen. So how are we going to balance nitrogen? We're going to put a 3 right there. Now, when we balance equations, we put big numbers in front of the molecular formulas. We do not put it down here. Because if we put it down here, then we change the total reaction. So we put a big coefficient right out in front. And so now we have 3 nitrogens. Whoops. Why did I do 9? Oh yeah, sorry. My bad. Let's start with nitrogen. But we're just not going to do that. When we don't look at our notes, this is what happens. So let's put a 3 out here. So now we have 3 nitrogen. How many hydrogens do we have? There's 3 here. There's now 3 here. So we have 6 hydrogen. And how many oxygen do we have? We have 9 plus 3 is 12. Okay? But our nitrogens are now balanced. We have 3 and 3. So what do we want to do next? Because remember, we want to keep oxygen last. Let's do hydrogens, right? So we have 6 hydrogens over here. How many hydrogens? We have 2. So if we put a 3 over here, we now have 6 hydrogen. We have 9 plus 3, we have 12 oxygens. And both of those things match up, and it is the simplest coefficients. Now, we could have put a 4, a 12, a 4, and a 12 there, and it would technically be balanced. But what we're aiming for is the simplest coefficients. And in this case, we have the simplest coefficients, and so we have successfully balanced this equation. Hopefully, we didn't scare you with all the math or the balancing. And again, with a lot of practice, it will be made perfect. We have a review day on Monday. So please come to that, bring your questions. We'll do probably a Zoom meeting sometime in the afternoon, maybe after the lab. Even during lab, I'll be able to answer some questions that you might have. As long as we stay distanced, we'll be able to answer your questions. So thank you guys again for chapter 3. I apologize that this one was a little bit long, but we had a little bit more math to do. And so that's okay. No, excuse me. And so if you have any questions, please let me know. Hopefully you've enjoyed chapter 3. As you do the homework, again, please ask me.